What's up, my friends? Welcome back to our data science journey. Today is day 6. We're diving into something super cool. It's called Exploratory Data Analysis, or EDA. Now, I know that sounds like a very technical, very complicated term, but trust me, it's not as scary as it sounds. Think of it like this. You've just been handed a mystery box. You don't just guess what's inside, right? You pick it up, you shake it, you feel its weight. Maybe you peek through a little hole. You try to understand it from every possible angle before you open it. That, my friends, is exactly what EDA is in the world of data. EDA is the art of having a conversation with your data. It's our first step as data detectives. Before we build any fancy models or make any big predictions, we need to understand the story our data is trying to tell us. It's about getting to know the characters, finding the plot twists, uncovering the hidden secrets. We look for patterns, we spot things that seem out of place, we ask a lot of questions. This process is super important. It helps us form ideas, or what data scientists call hypotheses. It guides our entire analysis and ensures we don't jump to the wrong conclusions later on. So why should you care about EDA? Because this is where the magic truly begins. So grab your virtual magnifying glass, put on your detective hat, and let's get ready to explore. To develop our analytical skills, we require a compelling case to investigate, and few mysteries are as renowned as one of the most significant events in modern history. We will be examining the Titanic Dataset. Yes, the Titanic, the so-called unsinkable ship. It met a tragic end on its maiden voyage in 1912. The story is familiar to many, marked by drama, heroism, and heartbreak. Yet beyond the cinematic portrayals and historical accounts, there is a narrative revealed through data. The records of the passengers from that fateful night have been compiled into a dataset that is now a classic resource for data scientists worldwide. This dataset serves as a time capsule. It contains detailed information about more than 800 individuals who were aboard the ship. Details such as name, age, gender, and class, first, second, or third, are included. The dataset also records where each passenger boarded, how many family members accompanied them, and most crucially, whether or not they survived. This is far more than a collection of arbitrary numbers and names. Each row in this dataset represents an individual with a unique story, someone with aspirations and dreams whose life was forever altered on that cold April night. Analyzing the Titanic dataset is impactful because it connects us to a real historical event, making the implications tangible. The survived column is not merely a 0 or 1, it represents matters of life and death. This context lends greater significance to our analysis, allowing us to pose profound questions. For example, did being a woman or a child truly increase the likelihood of survival, as the Women and Children First protocol suggests? Did first-class passengers have a greater chance of reaching a lifeboat compared to those in third class? These are the questions we will seek to answer. The dataset is celebrated in the data science community for good reason. It is sufficiently complex to be engaging, yet accessible for those new to the field. It includes numerical data such as age, textual data like names, and categorical data such as passenger class. As we embark on this digital exploration of the Titanic, let us remember that we are not merely analyzing data, we are honoring the lives behind the numbers and striving to learn from their stories. Let us begin our investigation. All right, team. Our first task as data detectives is to clean up our crime scene, or in this case, our data set. Real-world data is almost never perfect. It's often messy, incomplete, and full of little errors. Think of it like an old dusty attic you're exploring. You have to clear out the cobwebs and dust before you can see the treasures inside. In data science, this cleanup process is called data cleaning. One of the most common problems we'll encounter is missing values. This happens when some information for a passenger wasn't recorded. Maybe their age was unknown. The cabin they were in wasn't written down. Let's look at our Titanic data. A quick check will show us that some columns have missing values. For example, the age column has a significant number of empty spots. The cabin column is even worse, with a huge amount of data missing. So what do? We can't just ignore these gaps. They can mess up our analysis and lead to wrong conclusions. We have a few options. For a column like cabin where most of the data is missing, trying to guess the values would be too risky. It's often best to just remove that column from our analysis for now. It's sad to lose that information, but it's better than making things up. But what about the age column? It has some missing values, but most of the data is there. Deleting the whole column would mean losing a lot of valuable information. Age seems like a really important factor in survival, right? So we need a smarter approach. One common technique is called imputation. This is a fancy word for filling in the blanks. We can't know the exact age of those passengers, but we can make an educated guess. A simple and effective way to do this is to fill the missing spots with the average age of all the other passengers. It's not perfect, but it's much better than leaving the gaps or deleting the whole column. Let's see how this looks in code. Using a library like Pandas in Python, we can easily find the average age and fill in the missing value. A simple line of code like df_age, fill that df_age, mean, in case equal sign true, does the trick. See? Not so scary. Now that we've handled the empty spots in our data, let's talk about another combination, outliers. What are outliers? They are the odd ones out, data points wildly different from the rest. Imagine passenger ages mostly between 20 and 40. Then one shows as 200 years old. That's almost certainly a mistake, an outlier. It could be a typo or error. Outliers can seriously skew results, especially averages. Friend salary, 50,000. Friend salary, 60,000. Friend salary, 55,000. Friend salary, 70,000. Friend salary, 65,000. Average is about 60,000. Now one friend earns 1 million. New average shoots to over 200,000. That average no longer represents most friends. The outlier distorted the picture. Same with our Titanic data. An impossibly high fare or wrong age can throw off what's normal. How do we find these outliers? Visualization. One of the best ways. A box plot is fantastic for spotting outliers. Okay, our data is clean. Now it's time to start summarizing what we have. This is where we use something called descriptive statistics. Don't let the name intimidate you. It's a simple way to describe the main features of our data using numbers. The three most famous descriptive statistics are the 3 M's, mean, median, mode. They're super useful for data detectives. They give a quick snapshot and show the central tendency. Let's start with the mean. The mean is the average. Add values and divide by count. For Titanic, we could calculate the mean age of passengers. That gives a single representative age, about 29 years old. Handy. In Python, df_age mean. Next, the median. The median is the middle value when numbers are ordered. With 9 numbers, it's the 5th. Useful because outliers don't sway it. Finally, the mode. The mode is the most frequent value. Great for categorical data. Example, embarked column. Ports where passengers boarded: S, Southampton; C, Cherbourg; Q, Queenstown. The mode shows the most common port, DF embarked mode. Together, mean, median, and mode give us the first clues to the big picture. Numbers like mean and median are great, but sometimes they don't tell the whole story. As humans, we are visual creatures. We understand things much better when we can see them. This is where data visualization comes in. It's the art of turning our data into charts and graphs. This makes it way easier to spot patterns, trends, and relationships that might be hiding in the numbers. Two of the most basic but powerful types of charts are histograms and bar charts. They look similar, but they are used for different kinds of data. Let's start with a histogram. A histogram is used to show the distribution of numerical data, like age or fare price. It groups the numbers into ranges, or bins, and then shows how many data points fall into each range. For example, we could create a histogram of passenger ages. This would show us how many passengers were between 0 to 10 years old, how many were 10 to 20, 20 to 30, and so on. This is so much more powerful than just knowing the average age. It would immediately show us that there were a lot of young adults on the ship and very few elderly people. We can create one easily with code like df bracket age bracket dot heist parenthesis close parenthesis. Now let's talk about bar charts. A bar chart is perfect for comparing categorical data. Peace class column, first class, second class, third class, sex column. We can't take an average of first class and third class. Instead, we want to count how many people were in each category. A bar chart is perfect for this. We could create a bar chart showing the number of male and female passengers. Another one could show the count of passengers in each of the 3 classes. This gives us a very clear instant comparison between groups. The real magic happens when we start combining these ideas. For instance, we could create a bar chart that not only shows the number of people in each class, but also colors the bars based on whether they survived or not. Suddenly, a story starts to emerge. We might see that the bar for first class has a much larger proportion of survivors compared to the bar for third class. This is a huge insight. We've just visually confirmed a major factor in survival. Let's add another powerful visual tool to our detective kit, the box plot. This one might look a little strange at first, but it is incredibly useful and packed with information. A box plot, also known as a box and whisker plot, gives us a 5-number summary of our numerical data, all in one neat little package. Minimum value, the maximum value, the median, which is the line inside the box, first quartile, third quartile. These quartiles basically divide our data into 4 equal parts. The box itself contains the middle 50% of your data. A short, squat box means most people are clustered around the median. A tall, long box means the values are much more spread out. Let's apply this to the Titanic. We could create a box plot to compare the ages of passengers across the different passenger classes. This simple chart allows us to compare distributions between groups at a single glance. Our final visualization tool for today is one of my personal favorites, the heat map. A heat map shows relationships between numerical variables all at once. It sounds complex, but the idea is simple. It's a grid where each cell's color shows the strength of a relationship. Think of it like a hot and cold game. Bright, hot colors, like red or yellow, mean a strong relationship. Dark, cool colors, like blue or purple, mean a weak relationship. To create a heat map, we first calculate a correlation matrix. In Python, one line in Seaborn does it, essence.heatmap, df.core, a not equal sign true. On the Titanic heat map, we might see a negative correlation between per class and fare. That makes sense. As class number increases from first to third, fare tends to drop. We can check survived against other variables. So, let's take a breath and look at what our detective work has uncovered so far. We started with a messy, raw dataset, a digital ghost of a famous tragedy. We cleaned it up by handling missing ages, making our data more complete. We learned how to spot outliers, those strange data points that could be errors or important clues. We then used descriptive statistics to get our first summary of the passengers. Average age, the most common port they embarked from. These were our first steps in understanding the people on board the Titanic. Then, we brought the data to life with visualizations. Histogram, age distribution, bar chart, passenger class counts, box plot, age by class, heat map, correlation overview. Our histograms showed us the age distribution, revealing a ship full of young adults. Our bar charts gave us a clear picture of the stark inequalities on board. We visually confirmed that third class had by far the most passengers. When we added the survived variable to our charts, the story became even clearer. We saw that passengers in first class had a much higher survival rate than those in third class. We also saw a dramatic difference in survival rates between men and women, strongly suggesting that the women and children first protocol was indeed followed. Our box plots allowed us to compare distributions, hinting that first-class passengers were generally older than those in third class. And our heat map gave us a high-level overview of all the numerical relationships, confirming the link between passenger class and the fare they paid. We haven't built a single predictive model yet, but look at how much we already know. We have explored the data, we have asked questions, and we have found some incredible initial insights. This is the power of exploratory data analysis. It's about building a story, piece by piece. This is just the beginning, my friends. What we've done today is lay the groundwork for the next, even more exciting phase: feature engineering, model building. Now that we understand our data, we can start creating new features from it to make our future predictions even more accurate. I hope you're feeling empowered and excited. You've taken raw data and turned it into a narrative. Keep that curiosity burning. Until then, keep exploring.